Hello. This video recounts the thrilling adventures of porting my Game Boy sound engine to the Game Boy Advance. If you enjoy reading, there is an article version linked in the description. The article contains links to the various parts of code that we will look at. The sound engine is what powers the recordings found on this YouTube channel. How the original NES sound engine was ported to Game Boy was described in the video and article linked in the description. Check it out if you haven't already, so that you'll already be familiar with the Game Boy sound hardware, the song format, and the sound engine architecture. I'll wait here until you're done. The initial objective and key result of this project was to take the Super Mario 64 main theme Game Boy version, linked in the description, and make it sound good on Game Boy Advance, preferably identical. The result can be found in the GitHub repository linked in the description. The README file contains instructions on how you can build the ROM file yourself. Game Boy vs. Game Boy Advance hardware. Sound. The Game Boy Advance includes 4 legacy sound channels that are inherited from the original Game Boy, 2 square wave channels, 1 waveform channel, and 1 noise channel. Perfect, just what we need for making a one-to-one port of the Game Boy sound engine. What could possibly go wrong, I wonder? Additionally, the GBA has 2 so-called direct sound channels, which can play 8-bit PCM sample data. At first, I thought that utilizing the GBA's direct sound channels would be outside the scope of this porting effort. While the engine could be extended to support these channels, the purist in me renounces the idea of utilizing general-purpose digital audio waveforms, as it arguably takes the charm and challenge away. However, due to a behavioral difference between the Game Boy Advance and the original Game Boy sound hardware, I've had to backtrack on this decision. More on that later. A big appeal of the legacy sound channels is that they require at most a few hundred CPU instructions in total to program one frame, approximately 1/60th of a second, worth of audio. A sound mixer that's implemented in software requires orders of magnitude more CPU. Streaming PCM data from ROM requires storage. By utilizing only the legacy sound channels, those precious resources can be spent on other things, such as rendering advanced 3D graphics. CPU. Recall that the Game Boy CPU is an 8-bit microprocessor that is a hybrid design based on the Zilog Z80 and Intel 8080 CPUs, running at 4.19 MHz. The GBA uses a 32-bit ARM CPU, running at 16.78 MHz. It supports both 32-bit and 16-bit, so-called thumb, instruction sets. In the initial conversion, I've chosen the 32-bit instruction set for simplicity and performance. Memory. The Game Boy has 8 kilobytes of work RAM and 127 bytes of high RAM. The GBA has 32 kilobytes of internal working RAM and 256 kilobytes of external working RAM. In this project, I've only made use of internal working RAM. 32 kilobytes still feels extremely luxurious and I try not to waste it. Memory mapped I/O. Like the Game Boy and the NES, the GBA uses memory mapped I/O for, among other things, programming the sound hardware, configuring the graphics hardware, and reading the joypad. Additionally, the GBA has powerful direct memory access support that enables hardware-assisted, lightning-fast, memory transfer between any parts of memory. Graphics. The GBA supports tile-based graphics modes, like the original Game Boy and the Game Boy Color, only more powerful, but also bitmapped frame buffer modes, with 15-bit or 8-bit index colors. To minimize CPU time spent on drawing, it's best to stick with the hardware-assisted tile-based modes when possible. Interrupts. Like the Game Boy, the GBA has a V-blank interrupt that can be triggered after each frame has been rendered. This is where we will put all our per-frame logic. Read the joypad. Update sound. Update objects. Write sprites to object attribute memory. And write tilemap data or bitmap data to video RAM. Step 0. Getting started with Game Boy Advance development. The very first step, before it's possible to even think about how to port the sound engine, was to find a tool chain and get a Hello World GBA program up and running. When I asked ChatGPT which tool chain is recommended for modern GBA development, they suggested ARM None EABI GCC. Cool. We can use vanilla GCC, no custom or proprietary tools needed. Finding or writing a Hello World program written in assembly language turned out to be the first challenge. ChatGPT's minimal example produced a ROM that failed to load in the MGBA emulator. With the help of a few guides and repositories for development in the C programming language, I was able to cobble together a linker script that produced a ROM with a valid header. The joy of seeing a line of self-painted pink pixels on the screen was short-lived. Time to move on to the real task at hand. Step 1. Getting to know the GBA sound hardware registers. The registers of the legacy sound channels have gotten new names, and are 16 bits wide instead of 8 bits, but their contents and behaviors mostly correspond one-to-one to the original Game Boy registers, except for one agonizing, hair loss-inducing crucial difference, which we'll get back to. Like I had done when porting the NES sound engine to the Game Boy, I proceeded to write a small test program that produced sound on each of the 4 legacy sound channels in the simplest way. This gave me an idea of what I needed to work towards to materialize sound in the new engine. I decided to separate the sound engine into its own assembly file this time, so that it can be assembled independently of the rest of the program. Step 2. XM2GBA. Like XM2NES before it, the XM2GB command line utility converts an extended module file into the Game Boy sound engine's own format, represented as a Game Boy assembly file. I adapted XM2GB to produce an ARM assembly file instead. Say hello to XM2GBA. At some point, I should unify the NES, GB, and GBA converters into one application, with a parameter that specifies the desired output format. There are a few space optimizations and bug fixes in the GB converter that haven't yet been backported to NES. Changes to song header layout. With the ARM CPU, data in memory must be aligned according to their size. 32-bit data on 4-byte boundaries, and 16-bit data on 2-byte boundaries. To achieve the required alignment with minimal amount of padding between fields, we can order fields according to their width. First, all 32-bit word fields, followed by 16-bit half-word fields, and finally the 8-bit byte fields. On the GBA, in 32-bit ARM mode, pointers are 32-bit. We must ensure that the pattern pointer table is aligned on a 4-byte boundary. The assembler will insert padding before the table if needed. The song header follows immediately after the pattern pointer table. On the Game Boy, the song header looked like this. On the GBA, the song header looks like this. The pointers to the instrument table and pattern table are placed first. They are guaranteed to be 4-byte aligned because the preceding table of pattern pointers is already aligned. Step 3. Porting the sound engine code. Overall, this was a lot easier than porting the NES sound engine to Game Boy, despite Game Boy assembly and GBA assembly being just as different. I had the Game Boy code and the GBA code open in the editor, side by side. I painstakingly ported one instruction at a time, in a mostly mechanical fashion. Further optimizations are left for later. Subroutine names, variables and other labels were kept identical to the Game Boy version. In this process, I even discovered some quirks in the Game Boy sound engine that will be corrected. Local labels in GCC. One annoyance with the GCC assembler is that it doesn't allow human-friendly local labels. You have to use names like 1, 2, 3, and so on. In any non-trivial subroutine with lots of branch logic, this can get out of hand. Suddenly you've accidentally branched to the wrong label. I strive to use local labels only in cases where the jump was very short, and avoided branching back and forth between multiple local labels. Instead, I used a convention of prefixing pseudo-local labels with the name of their parent label to make them both unique and descriptive. Changes to track layout. As with the song header, I changed the layout of the track data structure to satisfy alignment requirements on ARM. If you recall, this is what the track layout looks like on the Game Boy. This is what the track layout looks like on the GBA. Words. Then half words. Then bytes. Indexed addressing modes. I'm sure you all remember from the video about the NES to Game Boy port, that my biggest gripe with the Game Boy CPU is that it doesn't have any indexed addressing modes, either by register or by constant offset. Fortunately, the GBA CPU supports both. This meant that I didn't have to spend time organizing fields in the supposedly optimal temporal order. It also means that field access is self-documenting. I'm free to reorder, add, and delete fields at any stage without existing code being impacted in unpleasant, downright agonizing ways. I did try to be clever by only writing pointer registers back to memory strictly when needed, but initially missed a couple of spots. This was the source of a few intense debugging sessions, since the stale pointer typically only manifested in a glitch or crash several frames later, when the next pattern data were read from the wrong address. ARM is RISC. With the ARM instruction set, it's not possible to perform operations, such as arithmetic and bitwise, directly on data in memory. You always have to load data to a register, perform the operation on the register, then write data back to memory. Such is the nature of a RISC, reduced instruction set computer, microprocessor. With the original Game Boy CPU, operations mostly have to be performed on the accumulator register. It's cumbersome that adding a value to the E register takes minimum 3 instructions. Move E to A, add value to A, and move the result to E. If you wanted to preserve the original value of A, more instructions are needed to save and restore it. However, there are a few Game Boy instructions that can operate directly on the memory pointed to by the HL register. These can be used to test, clear, and set bits, shift and rotate, and increment and decrement 8-bit data in memory without the use of an intermediate register. The ARM CPU can't do this. On the other hand, ARM has 13 general-purpose registers, not one special accumulator register, that can be used by any instruction. So far, the GBA sound engine didn't have to use more than 6 of the general-purpose registers at most. Updating status flags in ARM instructions. A nice feature of the ARM instruction set is that you can choose whether certain operations should update the status flags. Adding an S suffix to the instruction mnemonic will cause status flags to be updated. Add does not update flags. Adds updates flags. On the Game Boy, you might recall that I complained about the AND, OR, and XOR instructions causing the carry flag to be set to 0. How is that useful when there are dedicated instructions to set and clear the carry flag? Similarly, on the NES 6502 CPU, the load instructions, LDA, LDX, and LDY, are rather unique in that they update both the 0 flag and negative flag. I like that the ARM instruction set makes the behavior explicit in the instruction, though I admit it takes me a while to remember to use sub S instead of sub when decrementing a loop counter. Linker script. Once it's written exactly the right way, the linker script that defines how sections of object files produced by the assembler should be mapped to ROM and RAM works wonderfully. In the initial version of XM2 GBA, there was a bug that made it produce this line, .section row data, instead of this line, .section.row data, in the assembly output. GCC was totally fine with this .section row data, and the linker seemed to be too. No warnings or errors were produced. I couldn't understand why the data didn't end up in ROM. But row data is of course a totally different section than .row data. The default behavior of the linker is to place unknown sections at the end of the output, without warning. Here the discard directive comes to the rescue. This gives us the desired behavior of the linker failing with an error that says which section was discarded from which object. Debugging. The GBA emulator provides a set of tools that are useful for development. A debugger that loads symbol files and viewers for memory, graphics, and I/O registers. One weakness compared to the same Boy emulator is that the memory viewer in GBA doesn't automatically refresh when stepping through code. You have to click on a cell in the viewer to refresh it. Visual Boy Advance M is another emulator that provides a similar set of tools, and it provides an option for automatically updating the view. ROM header checksum. When the GBA BIOS is enabled, the program doesn't start in the Nano Boy Advance emulator unless the checksum in the ROM header is correct. If the checksum is wrong, the program will silently halt at the startup screen. A script, such as this header.py, can be used to repair the checksum, similar to the RGB fix tool that we use in Game Boy projects. ROM size. If you recall, the minimum size of a Game Boy ROM is 32 kilobytes. If the program and data occupy less space, the ROM must be padded to reach a size of 32 kilobytes. In Game Boy projects, we can use the RGB fix tool to achieve this. This is a bit sad when our program could actually fit in 16 kilobytes or less. For GBA ROMs, there is no minimum size constraint. Padding is not needed. Currently, the size of the Super Mario 64 main theme remix ROM is around 17 kilobytes. Step 4. Check the results. Testing on emulators. There are several popular Game Boy Advance emulators, and we should aim to get similar results on all of them. This will also increase our chances of the output sounding the same on a real GBA. Unfortunately, the sound output currently differs between emulators. On Visual Boy Advance M, it sounds as I hoped it would. On the GBA emulator, the volume envelopes don't behave as desired. Recall from the Game Boy port that I relied on an undocumented feature of the sound hardware, zombie mode.
Grr, arg.
As luck would have it then, this behavior enables the channel volume to be modified without retriggering the waveform. This is essential to achieve when volume envelope interpolation is implemented in software. Software envelopes give more precise control of the volume than what the hardware envelopes can provide. Here's what it sounds like on GBA when volume envelopes are not working. In GBA's Game Boy Color compatibility mode, the zombie mode emulation was improved. The original Game Boy version of the Super Mario 64 main theme therefore sounds good. In the Nano Boy Advance emulator, the output is about as bad as in GBA. However, there is a claim in this ticket on GitHub that zombie mode does exist on the GBA, and there is a discussion about how it can be added without regressing sound emulation in a few games. Testing on real hardware. Unfortunately, based on my own testing using an Easy Flash Omega cartridge, zombie mode does not appear to exist in native GBA mode on the original Game Boy Advance, model AGB001. Or, I'm not writing to sound registers in the required way. Zombie mode works fine in GBC mode, so the hardware is capable of it. I've yet to test on the other hardware models, Game Boy Advance SP and Game Boy Micro. But the odds of zombie mode working on those units are slim. Alternatives to zombie mode. If we re-trigger the channel on every volume change, the result does not sound good. We get a rasping effect. ChatGPT would have me believe that there is an alternative to zombie mode that lets us alter the volume without re-triggering the channel. However, when I pointed out that this information contradicted their previous statements about how the hardware works, they were quick to admit their mistake. It's hard to accept that I most likely have to ditch my software-managed volume envelopes in favor of the more limited hardware-supported envelopes. Or, I will have to drop all legacy channels except the waveform channel, which has a different mechanism to control the volume, and implement a software mixer. I wish that the Game Boy and Game Boy Advance had treated channel volume the same way as on the NES, where you can freely change the volume without fear of re-triggering the waveform. Conclusion. Well, there you have it. The GBA is a powerhouse compared to the original Game Boy, while mostly retaining support for the classic sound hardware. The GBA can be programmed using Libre software, GCC. The ARM instruction set is pleasant to work with. Zombie mode doesn't appear to exist in native GBA mode, meaning that a different solution must be found for supporting precise volume control. Thanks for watching and supporting this channel. See you in the next update.
Grr, arg.